Welcome to video 22, 4.2 area, part 2. Today we're going to look at how we can use summation formulas to express summations without summation notation. So we are going to use these formulas. The good news is you do not need to memorize these 4 formulas, but you need to know how to use them. But to get started, let's just go back and review some limits. All right, so let's find the limit of s of n as n approaches infinity, where s of n equals this right here. So go ahead, set up your limit notation. So the limit as n goes to infinity of s sub n, equals this. So the limit as n goes to infinity of n squared plus n over 2n squared. I just multiplied that through. So go through, see if you can find the limit, and we'll check back answers in a second. Okay, so here's what I got. I was able to break up the limit here. N squared over 2n squared is 1/2. N over 2n squared is 1 over 2n. Now we can use direct substitution. Up here we could not because we would have infinity over infinity, and that doesn't work out. So cleaning it up, and then using direct substitution, we have 1/2 plus 1 over infinity, and we all know 1 over infinity is 0. So in the end, we get the limit to be 1/2. The next example is where we're going to use that table up above to use those summation formulas to rewrite an expression without the summation notation. So we're going to get rid of that summation right here, okay? And in the end, we'll find the sums for when n is 10, 100, 1,000, and 10,000. Okay, so first thing we want to do is we want to somehow rewrite this summation notation and eventually get rid of this notation here. So I gave you a hint. Let's separate this into 2 functions. One thing to keep in mind, n is a constant, okay? So I'm going to zoom in here so we can kind of talk about that. So since n is the constant, I factored that out, okay? So here's our original, and you can see that I factored 1 over n squared out because, again, n is a constant. So we're left with the sum from I goes to 1 to n of 2i plus 1. So what we can do is, just like with any addition or subtraction, we can split it up, okay? So we can write this as to 2 separate summations. So I still have 1 over n squared times the sum from 1 to n of 2i plus the sum from 1 to n of 1. And what we should notice is if you look above, something written in this form, when I have 2i or even just I, okay, this looks like the number 2 formula from above. If you take a look here, I just have a constant c, so this stems from the first formula up above. So if you take a look, the first part is this formula number 2, okay, where we have the sum from 1 to n of I. The second part, the green down below, is the sum from 1 to n of a constant c. So what we're going to use is we're going to, instead of having the summation notation, we're going to put that constant times n, and that goes in the green, and we're going to have n times n plus 1 over 2 in for the blue. So now when we go through and we make those substitutions, all we have to do from here is clean it up. So we've used those formulas to get rid of the summation notation. When we do, the 2's are going to cancel here, distributing n squared plus n, and then we have this plus n here, gathering all of the like terms, and then what we can do is we can distribute this 1 over n squared, and in the end, we get our summation formula we get our sum without the summation notation, and so s of n is equal to 1 plus 2 over n when all is cleaned up. So now what we can do is we were asked to find the sum for when n is 10, 100, 1,000, and 10,000, and now we're simply plugging into our formula here to get all of these values off to the side. Take a look and let me know if you have questions of how we got these values. Example 3, find a formula for the sum of n terms. Use the formula to find the limit as n goes to infinity. So we're going to kind of take what we did in the previous example, but now we're going to throw a limit in there. Okay, so we're essentially finding the sum when n goes to infinity, and this is leading us into some definite integrals, which we'll get into. So first, I want you to see if you can figure out how to first get rid of the summation notation using some of these formulas up above. All right, so give it a try to get rid of this summation notation with those formulas. Remember, n's are constants, so any constants that are in there you can pull out as coefficients, okay? You just have to leave any i's within our summation notation. Give it a try, let's see what you get. Okay, so what I was able to do was I factored out the 2 times 2, or 4, and the n times n squared. Remember, these are all constants, so those can be pulled out front. That just leaves me with the sum from I to n of, from 1 to n of I. So what we should recognize is this stems from formula number 2 in our table up above, okay? So all we're going to do is make that substitution. Instead of the sum of I, we're going to use that formula, and now we can clean things up, okay? So I distributed n times n plus, or n times 1, cleaned everything up. So now we're looking at the limit as n goes to infinity of 2n squared plus 2n over n squared. If we were to use direct substitution, it wouldn't work. We'd have infinity over infinity, so we have to break it up. 2n squared over n squared is 2. 2n over n squared is 2 over n. Now we can use direct substitution, and we get the limit to equal 2. This last example, we're going to use a little bit of what we talked about in the previous video, along with what we are doing today in this video with those formulas. So we're going to use the limit process to find the area of the region between the graph of y equals x squared plus 1 and the x-axis over 0 to 3. So I shaded that region. We want to find the area of the shaded region, okay? So what we're doing is we're essentially taking rectangles like we did in the previous video. But these rectangles, typically we talk about n rectangles. This time, we want those number of rectangles to go to infinity. So they're going to be super duper duper skinny all the way throughout, if you can visualize that, okay? A bunch of skinny, 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 skinny rectangles. Okay, so let's think about the last video we talked about. In order to find that right-hand sum or left-hand sum, we talked about the area of each rectangle. And we were adding those rectangles up to get the total area, okay? So delta x was our change in x. F of ci was the y value when we plugged that right endpoint or left endpoint into our function, okay? All right, so we're thinking this. We want the area as the limit of n goes to infinity, because we want those rectangles, the delta x, to get super duper small, okay? And we're taking the sum of all of these. So let's just remind ourselves, ci is going to be the start of our interval plus our delta x times I. Now, in this case, we're going to use our right-hand sums because they're a lot easier to deal with, okay? All right, so delta x is going to be our interval divided by n, right? The number of rectangles. Well, n is going to infinity, so we're going to leave it in terms of n. F of ci, well, if we take a look, c sub I is simply our delta x times whichever triangle we're on, or rectangle we're on. So 3 over n I is our c sub I value. So when we plug this c sub I into our function, y equals x squared plus 1, we're going to get 3i over n squared plus 1, or simply ni squared over n squared, 9i squared over n squared plus 1. Okay, so now we're going to plug in our delta x and our f of ci into our summation. And so the area under this curve is going to equal all of this work here. So we want the limit as n goes to infinity, the number of rectangles are going to be infinite, of the sum from 1 to n of our delta x, 3 over n, times f of ci, 9i squared over n squared plus 1. And now we're going to break it up, okay? So what I did was I multiplied 3 over n times each of these guys inside, and then I broke it up from the addition sign. So we get the limit as n approaches infinity of the sum from 1 to n of 27i squared over n cubed plus the sum from 1 to n of 3 over n times 1. Now we've got our two sums. I'm going to take out any constants and throw them into the coefficient. So we have the limit as n goes to infinity. We bring out the coefficient of 27 over n cubed. We're left with the sum of I squared. I take out the 3 over n in the second summation. We're left with the sum of 1. So looking above at the formulas, this formula is the same as formula number 3. So we're going to make that adjustment. And this guy goes with formula number 1. So now making that substitution in, we have gotten rid of our summation notation. And now it's just a matter of cleaning everything up. Okay, so take a look. You can pause the video. Make sure you understand the algebra that's involved. And what you should get in the end is the limit is equal to the best number in the world, number 12. If you have any questions on this information or on this video, make sure you ask in class next time we see each other.